In this lesson, we're going to look at more of the quantitative aspects of the gas behavior and specifically look at the ideal gas law, as well as using the ideal gas law to solve problems. The ideal gas law is an equation, PV equals nRT, that was determined through many experiments looking at relationships between pairs of variables. We're not going to get into how the ideal gas law came to be. We're only going to look at the final result and see how we can use it to understand and predict gas behavior. First, we need to identify all of the variables in the ideal gas law as well as the units typically used for those values. First, we're going to look at the pressure, and that's in units of atmospheres or ATM. Next, we have the volume, which has units of liters. N represents moles of our sample. R is the ideal gas constant, and so this was determined experimentally, and the value we will use most often for this is 0.08206 with units of liters atmospheres per mole Kelvin. There are other values for R, but they have different units associated with them. Last, we have our temperature, which is in units of Kelvin. Whenever we're doing calculations with gas laws, the temperature must always be in Kelvin. Unlike many unit conversions, when we convert between two units such as milliliters to liters or feet to inches, we're multiplying or dividing by some factor to understand the relationship between them. Converting between Kelvin and Celsius is a little bit different because we are adding a number to it. Kelvin is the temperature scale often used in science, and so 0 Kelvin is the absolute zero. We cannot get below 0 Kelvin. When we talked about isomers and we talked about molecules rotating and turning and twisting, we talked about them moving around. At 0 Kelvin, those molecular motions stop completely. Note that it is not degrees Kelvin, but it is just Kelvin. There is no negative Kelvin. 0 is as low as we go. The conversion from Kelvin and Celsius is fairly straightforward. We take the temperature in Celsius and add 273. So if we have 0 degrees Celsius, our temperature in Kelvin is 273 Kelvin. What if our temperature was 37 degrees Celsius? What would our temperature in Kelvin be? We take 37 degrees Celsius, add 273, and we get 310 Kelvin. Let's look at an example of how we would use the ideal gas law. Determine the volume occupied by 0.50 moles of CO2 at 0.975 atmospheres and 25 degrees Celsius. When we look at our equation, PV equals nRT, we can see the variables that we need to have. We need to have all but one of them so that we can solve for our unknown. So pressure is given in the problem as 0.975 atmospheres. The volume is not given. This is what's being asked for in the problem, so we indicate that with a question mark. N is 0.50 moles. R is our ideal gas constant, 0.08206 liters atmosphere per mole Kelvin. And the temperature is 25 degrees Celsius, but remember we cannot leave it in units of Celsius. We have to convert it to Kelvin, so we add 273 and get 298 Kelvin. If you forget what units should be used in the ideal gas law, look at the units of the ideal gas constant R. Notice that the units, liters, atmospheres, moles, and Kelvin match up with the units of our other variables. Now we can plug the values into our equation. So we plug in the pressure. The volume is left as V because that's our unknown. We have N times the ideal gas constant and times our temperature in Kelvin. I'm going to leave the 0.975 times volume. On the right side of the equation, I multiply all those numbers together and get 12.227. I'm going to then divide both sides by 0.975 and we get 12.54 liters, but we need to round this to the correct number of significant figures, and because we have 0.50 moles, so we have 2 sig figs, our answer will be 13 liters. Another example using the ideal gas equation. How many moles of helium are in a balloon with a volume of 8.5 liters and a pressure of 1.1 atmospheres at 22 degrees Celsius? We look at our equation, PV equals nRT, so that we know which variables we need to determine. Looking at the problem, we want to determine the pressure, which is 1.1 atmospheres. Next, we look for the volume, which is 8.5 liters. N is our unknown because that's what we're looking for in the problem. R equals 0.08206 liters atmospheres per mole Kelvin because that's our ideal gas constant. And finally, we look at our temperature. So the temperature is given as 22 degrees Celsius. But remember, we cannot leave it in Celsius. We need to convert it to Kelvin, and what we get is 295 Kelvin. Now we can plug in our values. So we have our pressure times our volume equal to N, because we don't know what our value for N is for our moles. Then putting in the ideal gas constant. And finally our temperature in units of Kelvin. Multiply 1.1 times 8.5 and multiply the ideal gas constant by the temperature. And then we divide both sides by 24.21 and we get the moles equals 0.39 moles.